Sorry for that. Okay, we are live. Let me grab the link and drop it into the channel like I always do. And I've got nobody in the voice channel with me. That's great. No studio audience right now. That actually means it'll be more efficient. That's kind of the way that goes. So that's all good. Doesn't hurt anything. This is actually the February 4th Thursday lecture pre-recorded, so I can go do my under the knife thing. I'm just dropping the link in like I do. So link for Thursday is now there. And I'm going to go for about an hour right now, and then I got to flip over for my other class at 4, which is in an hour and 8 minutes. So we're going to see how far we can get on that. Okay, that's there. That's there. That's there. Blake's here. Hey, Blake. Blake, we got a studio audience. Our studio audience today is Balake, and that's it. Just me and Blake. So I'm gonna still rock and roll, Blake. Don't feel too much pressure, okay? On trying to carry the day or anything. Let's see. Just grabbing the lecture here real quick again. PowerPoint stuff. Okay. When Blake, my sound's okay, right? Blake, is my sound okay? I'll assume it is if I don't hear from you. I mean, I have to assume something, so that might as well be it. All right, I'm just getting myself to the right spot here. Here we go. There we go. Two's complement integers. This is how far we got. All right, we're on the text thing there. Okay, ready to rock and roll. So here's the deal. Are we cooking here? Yeah. When last we met, we were talking about representing integers and representing negative integers. And we talked about one's complement. And we said that we could try this idea of flipping all the bits and just seeing if that would work. And when we added them together, it was so close to, when we added a positive and a negative version of the same magnitude together, it was so close to being 0, but it was actually 1 off. So somebody said, well, what happens if we just treat the negation of a number as flipping all the bits and adding 1? Like if I'm going to negate a number, flip all the bits and add 1. And if I negate it again, flip all the bits and add 1. So that's kind of was the inspiration for two's complement, okay? Blake's out, so I'm all alone here again. It's all good. But here's kind of the bottom line with two's complement notation. Like with sign magnitude or one's complement, you do have to know how many bits you're using, okay? You can't just be generic. It has to be a fixed number of bits. And whenever you're dealing with positive numbers, if you think about this, they look exactly the same as unsigned, as sign magnitude, as one complement, right? They all look the same, which is 0, plus whatever else. The difference is that unsigned values can get bigger, right, than any of the signed values. Because with unsigned, when you get big enough that you've got a 1 in the leftmost bit, it's not a negative number. It's just that, extra big, a number 128 or bigger, kind of thing. But when you're dealing with anyway, unsigned, they look the same. They're just smaller than the maximum of an unsigned value. So here's the kind of the interesting question, right? When you're dealing with positive numbers, there's literally no difference other than the top value, the biggest value you can reach. With any signed value, the biggest positive number is half the size of what it would be. Hey, Gabe, for a sign value, right? Because you gave half of them away to the negative numbers. The dicey part is, how do you represent the negative numbers, right? And how do you negate numbers? And negating means you take a positive number, you make it negative. You take a negative number, you make it positive, okay? You're changing the sign, right? That is what negating, that's what it means when we, so negating is not to make a positive number negative. It is that, and also to make a negative number positive. So negating is a process of changing the sign of a number, okay? So in decimal, how do you negate a number? Easy. If it's positive, you add a negative sign. If it's negative, you either erase the negative sign, or some of you played this game in algebra, is you just like put a vertical line through it so it turns into a plus, you know? That's how you negate a number in our decimal system. In that's it. In binary, not gonna work. So as we already said, representing a positive number the same old boring way, we already know how to do it. Negative number. Here's how you do it. Okay, here is the recipe. It is very straightforward. This is how you negate a number in 2's complement notation. Okay. If you want to represent a negative number, you start with the positive magnitude number. You flip all the bits and you add 1. That's it. That now gives you the negative of that number with the same magnitude. Okay. That's 1. And if there's a carry out, you ignore it. Okay. Any carry out, that's really the third step. Flip all the bits, that's step number 1. Add 1, that's the next step, and ignore any carry out. By carry out, I mean if you've got 8 bits and there's a carry out of that last high order bit out, then you ignore it. Okay? That's it. And when you take that negative number and you negate it, meaning turn it positive, once again, you flip all the bits, you add 1, and you ignore any carry out. That's it. That's the Majike. Now, remarkably, there are students every semester who, even down the stretch, will write little code in assembly language and they'll flip all the bits. And then they'll say, and in the comment, it'll say, negate the number. Like, come on, man. Yes, you flip the bits, but then you have to add 1. You flip the bits and you add 1. It's weird, but it's like a little trick that you have to remember, and it works. Okay. So let's take a look. Let's do a couple of approaches here. There we go. 83, positive 83. All right. So we're going to start with that, and we're going to negate it. So we want the binary representation of negative 83. That's positive 83. You can work the math yourself, right? 1, 2, 4, 8, 16, 32, 64, right? So 64 plus 16 is 80, plus 3 is 83. You can see that it's 83, okay? We flip all the bits. Every 1 turns into a 0. Every 0 turns into a 1. We're going to find out later there's actually a name for this operation. It's called a not. But we flip all the bits and we add 1. Okay, check it out. 1 plus 0 is 1, and that just falls right. You know what I mean? Everything's the same. 1 plus 0 is 1, no carry, and then everything else just drops straight on. That is the representation of negative 83 in 2's complement notation. Okay? Now I want to be really, really clear about something, and I don't know why this persists, but I want to be clear about it at the risk of even creating a little bit of confusion. 2's complement is a notation. It is the name we give to a notation. 2's complement integer, or notation, or 2's complement notation. If I say this is a 2's complement integer, then it is an integer. It's signed, because 2's complement is a signed notation, meaning it can handle both positive and negative numbers, okay? It's a signed notation. And that's what we mean. A 2's complement integer is an integer represented in binary according to 2's complement notation. All right. Now, for some reason, everybody gets so, I don't know, scarred or terrified or freaked out about this whole flip all the bits that they sometimes will get confused, and people will say terms that's not correct, like take the 2's complement. No, take, you know what I mean? If this were decimal and I said I want you to negate, here's negative 83, I want you to negate it in decimal. You'd go, easy, 83. I wouldn't say take the decimal of it. You know what I mean? I would never say take the decimal of it. We don't say take the sign magnitude of something. We don't take the 2's complement of something. Okay? 2's complement is a notation that includes both positive and negative numbers, and it's the name of the notation. A 2's complement integer is not necessarily a negative integer. Okay? Might be, the same way that a sign magnitude integer might be a negative integer, or a 1's complement, or some other rando notation. Okay? Got that? 2's complement is the name of the notation, and it is the name of the social contract. The social contract is called 2's complement. And the social contract for 2's complement is very simple. It says if it's a positive number, just represent it like an unsigned integer, only you can only use 7 bits of magnitude. You can't spill into the leftmost bit, or you're going to change the sign, so that doesn't work. So if it's a positive number, it looks just like an unsigned value, only there's never going to be anything in the leftmost bit. If it's a negative number, then it is in a representation such that to see the positive value, or in other words, to see the magnitude, you would have to negate it to its positive to tell. It's almost like negative numbers, they don't jump right out at you. You can with some mind tricks, but I'm not even going to talk about it. But it turns out you can look at a negative 2's complement number, meaning a negative number encoded in 2's complement notation, represented by that. And you can't look at it and see what the magnitude is. You can only see that it's a negative number. So the answer is, I'm going to convert that number into a positive number. Now I'll know the magnitude. We're going to talk about that. So step number 1, draw a minus sign. Step number 2, negate it to make it a positive number. Now I see the magnitude, and now I know what it is. Okay? The trick with 2's complement notation is how you represent a negative number and how you negate numbers, move from positive to negative and from negative to positive, right? Sign magnitude, how do you move from negative to positive and positive to negative? You just flip the sign bit. That's all you do. Unsigned, how do you move from negative to positive? You don't. There's no negative. You don't move. It's always positive. 2's complement, how do you move between negative and positive? You flip all the bits and add 1. That negates it. Takes a negative number and makes it positive. Takes a positive number and makes it negative. Okay? Everybody got that? Everybody, Gabe, got that? Small studio audience. No pressure, Gabe. You don't have to say anything or even make comments, man. It's all good. Okay, so let's go the other way. We just did start with a positive 8-bit number and negate it. That's what we did there. Now we got this number right here, 10, 10, 1101. There it is, 1010, 1101. That's negative 83, right? Check it out. It's right there. I want to negate it, meaning I'm going to turn it positive. What do? I flip all the bits and I add 1. Boosh. Isn't that cool? And that's the same. That's the same value from before. In fact, if we go all the way back, right? See it? 0101, 0011, 0101, 0011. It just goes on indefinitely. The positive goes negative. You just flip the bits and add 1. Now flip the bits and add 1, flip the bits and add 1. If you do it an even number of times, you'll just always come back to where you are. If you do it an odd number of times, you'll wind up on whatever the other sign was. Isn't that cool? That's it. Okay. And for some reason, it's so spooky for some students that as soon as somebody says two's complement, they start going woo, 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 and they start like flipping bits and adding one. Oh, yeah, somebody said two's complement. You know, I got to start flipping bits. No, no. Okay. Let's do this one. Let's do this one. Now, I didn't animate this. It's just sitting here, but check it out. There's plus 83 and there's negative 83, right? I pulled these just right off the slides. So just trust or believe or remember that these were the numbers. That was positive 83. That's negative 83. Remember when we tried to take like sign magnitudes and add them together and see if we could get zero, and it was like a mess. One's complement, it was close, but not quite, right? Let's do this. Positive and negative of the same magnitude. 1 and 1 is 0, carry the 1. 1 and 1 is 0, carry the 1. 1 and 1 is 0, carry the 1. Feel a pattern. 1 and 1 is 0, carry the 1. 0, carry the 1. 0, carry the 1. 0, carry the 1. And then this is critical. In the 8th bit, you got a 0 and you carry a 1, but that carry is outside. That's the one that jumps off the cliff. Okay, we don't care about it. We ignore that carry out. By carry out, I mean there are 8 bits of there's 8 bits of representation. If you carry into the 9th bit, it just goes away and you ignore it. That seems weird. Seems like, wait, isn't that overflow? No, no, it's not overflow. In two's complement notation, again, social contract, how we do math, how we do addition in two's complement notation is that if we do addition and it goes out, that last one goes outside the carry, we ignore it. Okay? That's the contract. Weird, but true. Okay? Pretty cool. And by the way, Gabe, you know, there's literally no pressure on you, but if you do have any questions, we'll all know who it is. But if you do have any questions, either to drop in the chat or say it really, truly, like feel free. You have the burden of the studio audience. But you know what I'm saying? It's all good. So why do we do all that? Why do we do all that? You know, why do we drag you through all that? You know, to get to two's complement. Why pester you about the others? You know, one is the sign magnitude idea actually is still kind of an idea under certain circumstances. It does show up sometimes. One's complement mostly doesn't get used, but other than the fact that uh, it's to help you understand where these ideas come from. They're not just like, oh, the smart person just said the one thing, and now you just have to regurgitate the one thing, memorize the one thing, cram it into your head. There's a logical flow of these things if you follow them. Okay, so that's why we do it. Some other tidbits with two's complement. Notice, remember with sign magnitude, we had a positive and a negative 0. Remember that? The other interesting thing is that with one's complement, we also had a positive and negative 0. Two's complement, we don't. We don't have a negative 0. We just have 0. And so we just picked up a number, right? We don't have 2 zeros. We only have 1 0. So where's the extra number? Who gets the extra number? Should it be a positive number or should it be a negative number, right? And we already said, like with sign magnitude, we could go from positive 127 down to negative 127. Well, we're going to have a new value. It's either going to be positive 128 or it's going to be negative 128. Okay, we're picking up an extra number because we lost negative 0 and we can use, you know, that representation for something. What are we going to do? What are we going to do? The intuition here, which, you know, if we were all together, we could do a big discussion about this, but the intuition is the positive numbers already go. If you think of 0 as positive, as a positive number, the positive numbers already go from 0 to 127. The negative numbers, and how can you tell that 0 is a positive number? Gabe, you can answer if you want. The bit, right? The sign bit is 0. You understand that in a two's complement number, there's still a sign bit? It's just not dedicated. It's not dedicated like in sign magnitude. It's not just like flip that bit and we're done. But there is a sign bit. In two's complement notation, if the leftmost bit is 1, it is a negative number. And if it's 0, it is a positive number. So 0, by definition, in 2's complement notation, is a positive number because the sign bit is positive. Okay? So what are you going to do? What are you going to do with, where do you put that extra number? So 0 to 127 is 128 positive numbers. You've already got -1 down to -127. But if you think about it, the natural next spot is -128. You know what I mean? You're going to have 128 negative numbers now. You know, used to be you had 128 negatives from -0 to -127 and 128 positives from positive 0 to positive 127. Now we go 0 to 127, -1 to -128. There's still 128 negative numbers, but that's where we put it. And I'm going to skip that question for now. Is the high order bit still the sign? The answer is yes. Okay. And we're going to do a couple of tricks, okay? We're going to walk through a few things. So, here we go. This is one where normally we're doing the pre-recorder, but normally this would be audience participation. What's the largest positive 8-bit 2's complement integer? What's the largest number? And I need to check something here real quick. This is what we're going to go after right now. What's the largest positive 8-bit 2's complement number? That's a lot of words in that question, okay? But if you break it down, right, 2's complement integer means that it is in 2's complement notation. And we know that it's 8 bits. And what's the largest positive 8-bit value? What's the largest negative 8-bit value? And then what's the range? Those are always the questions when you get to Module 2, Module 3 exams. The questions are going to be, what's the smallest? What's the biggest? How many are there? And what's the range? Okay? Those are always going to be the 4 questions. Let's do the first one. What's the largest positive 8-bit number that you can represent in 2's complement notation? All right, let's take a look. Well, I already said it was positive, right? I know that the leftmost bit has to be a 0. I know that. Why? Because it's a positive number by definition. So what I've got basically is that so far. I got a 0 and 7 other things. Okay? What's the biggest number that can now be? And it ought to be pretty clear by now. Just, really what it's about is what's the largest magnitude you can represent with the remaining 7 bits? That ought to be pretty straightforward. Just they're all ones. That is positive, whatever that is. Okay? And you just do the math again. 1, 2, 4, 8, 16, 32, 64. This is 127. So it's positive 127. That's the largest positive 8-bit number that you can represent in 2's complement notation. Cha-ching. Okay. Let's do negative. Okay. Now we already talked about it conceptually, but let's do this thing because this one is the one that's a little bit funky. Let's do it again. What if we just took the biggest positive number, which we already know what it is, positive 127, and what if we just negate it? What if we just negated it? Let's try it. And by negate it, it's 2's complement notation. When you negate, you flip all the bits and you add 1. That's how you negate in 2's complement notation. So let's try it. There's 127 right there. 0 all the ones. Flip all the bits and add 1. And what do you get? Now just check your intuition about this. Check your intuition. That's a negative number. You know it's a negative number. And that is, just trust me, because we just did it, that's negative 127. Now we already said conceptually that the negative numbers were going to go from -1 to -128, and the positive numbers were going to go from 0 to +127. Always, we're talking about 8 bits right now. Is this bugging anybody? Gabe? Is this bugging you, man? Uh,
I had a question.
yeah, go.
So the way it works is like the one at the end essentially is it's a negative and it gives you the value of 128. So then the one on the other side, when you're counting in negatives, it's just you minus whatever is in the rest of the seven. You subtract that from the 128, and that's how you get it.
I didn't understand anything you just said, so either, so I don't know if I like missed it or if the question itself was wandering around. So I'm not sure what you're saying. You want
I think,
should we try again?
yeah, I was just, yeah. So when we were looking at the 83 versus the negative 83, I guess my brain was kind of confused on why the numbers didn't look like the exact same other than the one being at the front.
Oh yeah. And the reason is because you were my guessing, projecting in, I don't know. But it's probably because you were thinking of it like sign magnitude. Like they should look the same, but the sign is different.
Hmm.
But the reality is, and this is the goofy part about two's complement notation, is that when I negate a number in two's complement, they don't really look like each other anymore. You know, it's just like a weird encoding. Like I take that -83 and you trust me on that. Then I flip the bits, I add one, and I get this piece of crap right here. Actually, that piece of crap actually looks like the number 83 because it's positive. But if I go the other way, right? You know, you're like, oh, that's -83. Like, nah, none of that even makes any sense. I don't, you know what I mean? I can't like look at it and just intuitively go, you know, like with the 83, oh, there's a one, there's a two, you know, I can't do that with negative numbers in two's complement notation.
Okay, gotcha. I think that's what was just confusing me because I was trying to like count it out on like using that, and I was just like, how does
Yeah,
that add up to 83?
yeah. And the answer is it doesn't, right? It
Gotcha.
just like
Okay.
really doesn't. Um, so like this guy, no, it doesn't really make a whole lot of sense. I mean, if you're like a math head and you can run little tricks in your head, which some of the math people do, they're like, well, you know, actually, if you think of that as a Carnot map, you know, or I don't know, they have their, I'm making that up, but I've heard, you know, like, oh, you know, whatever. And there's always the math heads who have like this clever, and it's all great, great for the math heads, but maybe I'm just not one of them. And so for to me, I'm just like, too much work. I don't need to natively read a negative number in two's complement notation. You can always natively read positive numbers in all the notations, unsigned, sign magnitude, one's complement, two's complement, right? They all look the same. They're easy to read. Negative, nope. Does that make sense, Gabe? So,
Yeah, I get you.
you know, so it's really odd. But in this case, right, we already said conceptually we thought there was a -128, you know? You're like, okay, but if you look at this guy right here, that's -127. And if I made that number bigger, okay, this is a little mind trick just for a second. If I sort of like added one so that that became like 1 0, okay, instead of 0 1 at the very end. If I go right to the end, right? If I added one there and wound up with 1 0 at the very end, trust me on this, that would be -127. And if the last two were 1 1, that would be -125. See us going that way, right? So as these numbers get like bigger on the magnitude, you know, down at the right side, that number is getting like moving in the positive direction. It starts at -127, moving positive, -126, 5, 4, 3, 2, it's going that way. I already said conceptually there was a number hanging out way at the end called -128. How do I find it? Where is it? What is it? Because it's the one that sort of like doesn't kind of make sense. It's a weird sort of exception. But if we look at this and go, well, okay, if that's what happens when I start adding numbers down here on the magnitude, right, and that number moves to the positive, what if I subtracted that one and took it away, right? If I subtracted one out of that core number, what am I going to get? And the answer is, if you think about it, I'm going to get negative 128. But that's going to be a really, and you can think about it, you can get rid of that one and it's still a negative number, but all the rest are zeros, right? So I don't know if I've got, yeah, check it out, check it out. So I take this 120, this negative 127, and I was talking about adding one to the magnitude, but just subtract one now. Subtract one. Now, how do I subtract one? I take the number one, which is all zeros and a one. I flip all the bits. Now what have I got? All ones and a zero. I add one. Now what have I got? That number right there. All ones. So in two's complement representation, two's complement notation, however the number of bits are that you're playing with, that number, if it's all ones, is negative one. That becomes something you just remember. 8-bit integer and it's all ones, negative one. 16-bit integer and it's all ones, negative one. 3 bits for an integer, like 7, no, negative one. If it's two's complement notation, it's always negative one. Okay, so we take negative 127, we subtract 1 from it by adding negative 1 to it. 1 and 1 is 0, carry the 1, see where we're going, 0, carry the 1, bit, 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 bit. The carry out. And that's the representation for negative 128. Freaky?
So I think I figured out what I was trying to say in a little
Okay,
bit easier. So what I
yeah,
figured out, so looking at the 83 example, or uh, I basically counted up, ignoring the one on the end that signifies that it's a negative. I just counted all of the rest of them as if it was positive, and it got 45, and 128 minus 45 is 83. So I guess my understanding is that it's like subtracting from that, I guess.
yeah. And what you're doing, Gabe, is one of those clever math tricks that
Gotcha.
for 90+% of the students, including me, by the way, I can remember and go, yeah, no, that's right. And then my brain just goes, no, don't hang on to that. You know what I mean? It's not going to make it any easier. You know what I mean? And for some folks, Zach's probably one. It's just like, oh yeah, that way they can like look and it's all easy and they see in their head what the value of a negative number is in two's complement notation. And it's, you know what I mean? But for most
Yeah.
people, it's only just confusing.
Okay,
You know?
gotcha. Because I think that makes sense why all of the ones would make it a negative one, because, like you said, all of the ones leading up to the next big one is just the big one minus one.
Yep. Yep. Exactly. Now check this out. Now here's the thing with negative 128, which this just honestly, early in my time in my career, this just like bugged the crap out of me. It's just like, okay, looks like -0 to me. And you could almost, there is an element of that, like feels like we took -0 and we made that negative 128. Ah, wink, wink, nudge, nudge. But you're like, no, actually, actually, we derived this by taking negative 127 and we subtracted 1 from it. We didn't just like pick this pattern out of the air and go, oh, there's a leftover pattern. Let's let it be negative 128. You know what I mean? We actually took negative 127, which we could literally count our way down to that, and then subtracted 1 from it, which would get us to negative 128. And that's what it turned into. Like, so literally, even from a normal adder, right? Just add two's complement numbers together, ignore the carryouts. It just works. Crazy. Okay, and then here's the check. Let's take negative 128 and let's negate it. Now, okay, Gabe, what's the biggest positive number in two's complement notation?
127.
Yeah, positive 127. Now I'm asking you, if we negate negative 128, what are we going to get? This is the cool trick. Because you're like, 128? That doesn't exist. You're like, yeah, but no, we can't do 128, right? It doesn't exist. What happens if you take negative 128 and you try to negate it? Don't make any special rules. Just do the regular rule for negation in two's complement notation. There's our number. Flip all the bits. Add 1. What do you get? Ripple, 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 ripple. You get 1, and you carry, and there's a carry out that you ignore again, and you're back. Negative 128 when you negate it in two's complement gives you negative 128.
That's trippy.
Isn't that trippy? Okay, ready? Hubert cannot handle it. It's so trippy. That's crazy to me. Okay, now I understand that if you really like work it down, and you know what I mean, and do like the math, the number theory thing, and the mathematical core, whatever, you know, you can get down to it and go, no, that really works, but that's freakishly cool. That's just to prove that negative 128 is the proper representation. It works mathematically, but you can't negate it. You cannot negate it. Mind equals blown. Yeah, that's that crazy. It's so crazy. Okay, so that's our range of numbers. Okay, that's the range. In two's complement notation, the smallest number, if you will, or the largest magnitude negative number is another way of saying that. Is negative 128, and on the high end is positive 127. And this is also really, really important. If you get stuck at any point trying to remember, wait, one of these was more than the other, which one was it? Take it all the way down to a very small number, like a 4-bit number, and try it. Even a 3-bit number, and try it. And you'll brute force it, and you'll be able to tell what the pattern is. Then apply that, you know what I mean, to the bigger numbers that are harder to brute force. Okay. Now here's the key. We're going to do this really, really quick for 2 bits, 3 bits, 4 bits, and then we're going to talk about n bits, which is the generic form of this thing. And how am I doing here on time? I got to be hard stopped in about 20. Plus, I think I may have had like a phone call I'm supposed to return. In the gap, let me just see. This depends on how far I go. Okay, no, I'm actually good. I'm good. All right. Okay, great. With the surgery thing tomorrow, they're like supposed to call sometime when he's supposed to show up, all that. I don't want to miss that call. Okay, you ready? Here we go. Wait. Oh, no, sorry. This is an exercise to you. It's an exercise to the student. And really, truly, do this. Everybody should do this. Do it for 2 bits. Do it for 3 bits. Do it for 4 bits. And then start noodling. We already had that big discussion about n bits. Do it for n bits. Okay. The next part, and this is really, really important, very, very important, is moving between binary and decimal and moving from decimal to binary, meaning that I have this binary number. What is that number in decimal, right? Because we think in decimal. That's what we've grown up doing. And I got a decimal number that I need to turn into a binary number because I need to write a program that uses it, you know, whatever, maybe, right? So that conversion becomes kind of important. So here we go. These are the steps. Now, this should, everybody should do and spend enough time with this stuff that it gets to be a little more second nature. Practice it like a language, because you shouldn't like look at this and try to cram this. You know, it should be intuitive. If you really understand it, you don't need to cram it. It'll flow out. Okay. Number 1, check the leftmost bit, because you need to know if it's a positive or a negative number to start with. Okay, you're moving from binary to decimal. I look at it, and if it's a positive number, easy peasy. I got 7 bits to add up. Leftmost is 0, right? So that one right there, I'd go, okay, I got a 32. I got a no 16s, no 8s. I got a 4, a 2, no 1s. Boom, 38 decimal, right? Easy. We already know how to do that. But if that leftmost bit is a 1, it's a negative number. We know that it's a negative number. And we can't, unless we have superpowers, we can't look at it and just like see the magnitude. So we have to convert it to a positive number. We have to negate it into a positive number. My first step always at this point is write a minus sign on your paper. Write the minus sign So you don't forget that this is a negative number. You're just trying to find out what its magnitude is. So let's do it. Let's start with, I got a positive number, and this is what we do. So there's a number like 83. And these are the places, right? 1, 2, 4, 8, 16, 32, 64, 128. 2 to the 7th is 128. How many 128s are there? None. Okay. How many 64s are there in 83? There's one. By the way, the answer, spoiler, right, Gabe? The answer is always going to be 1 or 0. Okay. I take 83, I got a 64, I subtracted how much is left? 19. How many 32s are in 19? None. How many 16s are there in 19? There's one. There's your one. Subtract it out. I got 3 left unaccounted for. How many 8s are there in 3? None. How many 4s are there in 3? None. How many 2s are there? There's one. Leaves me one. How many 1s are there in 1? 1. Boom. That's 83. That's positive 83. Okay? That's what we've been doing. Now let's go negative. Okay? Let's do the decimal to binary, but we're going to convert it, but it's a negative number. Okay, number one is just find the binary representation for the positive version of the number. In other words, negate the number. Sorry. Oh, no, sorry. To convert a negative decimal number into binary. Sorry, back up. Yeah, we were doing decimal to binary. To convert a negative decimal number, we actually do the very same thing we just did as if it were positive. And now we know what the binary representation is, like right here, for that positive number. We do the exact same thing, only since it's negative 83, we would now convert it to a negative number by flipping all the bits and adding 1. Okay? So we just do 2 things we already know how to do. Okay? And the really critical thing is the intuition behind that. Okay? If I've got a decimal number like negative 83, I'm like, I need that binary. Well, let's just do 83 for starters, because I can do this process for 83 and I'll get that number. But that's positive 83. I need negative 83. It's like 2 steps, right? First, convert that decimal number into the binary version of the positive, binary representation of the positive version of that number. Now I have the positive version, negate it. Flip all the bits and add 1. Boom, now I got the negative number. So if it's a positive number, it's only 1 step, and if it's a negative number, it's 2 steps. So it's a little more cumbersome. Okay, that's it. Now, and I think this might even be the end of these slides. Amazing. So this is always a question I'm going to ask, which is, what is the range? Hey, Blake, what is the range of values you can store in 8 bits? And the answer, if I only ask you that question, what's the range of values you can store in 8 bits? The range, not how many. How many? 256. But that's not that. The question is, what's the range? Meaning from the smallest to the biggest, or the least or most negative, or to the most positive. And the answer is, it totally depends on the notation. Absolutely depends on the notation that you use. In unsigned, it's going to be, right, from 0 to 255. Signed magnitude, it's going to be negative 127 to positive 127 with a pair of zeros in the middle. 2's complement notation, it's going to be from negative 128, the crazy freakish mystery number, to positive 127. The range depends on the notation. Okay? Always, always, always. Okay, and amazingly, and this is actually probably good because I got to do a couple quick things before I jump on at my 4 o'clock class. And this is quicker. We've gone over many times. So this is a little bit of a compensation, but this is the end of module 2. End of module 2. Thursday's lecture, which means everything's due Saturday, homework, exams. So it's time to everybody should be playing bingo still. Jump on module 2 like a mad dog. and get the homework done, get the module exams done, get it cooked. Get in, get out, get ready for bingo on module 3. And by the way, I'm not going to start module 3 tonight. I've got to do a little bit of refinement on the slides that I'll try to do on the weekend, depending upon pain and narcotics. Could be a drug trip. And then before Tuesday, I'll post. Possibly under the influence, but we'll find out. We'll see what I can do. Anyway, that's it. That's module 2, man. Gabe, Blake, thanks for being my studio audience. We're going to send you home with our lovely parting gift for all of our studio audience members, um, which I don't even know what that is, but we'll come up with something. So that's it. Gabe, any last questions?
I think I'm good. Thank you so
All right, man.
much.
Thanks for keeping me company, Gabe. Extra bonus points for Gabe. Not really, but it's thanks for a little company. A little less lonely here, being the talking head, you know. So, all right, man. I'm out. That's it.
Alrighty, I'll see you in 305G.
All right, man. See ya.